make sure I'm recording. It's going to be online, available for download later. So even though some of the analysis setup is going to be quick and some of these are just going to fly through, you always have the opportunity to download this video later, pause it, rewind it, see what I was clicking, see where I set things. So take comfort that even if it goes fast, you have the opportunity to review this later on. Like I said, I have a couple other my colleagues on the line. So if you guys have questions during the presentation, and you guys got audio? I think I hear George.
I can hear you, Adrian. Hi, this is George Blair. So, yeah, I'll be online answering questions. And I want to mention we've been using the Solution 106 for probably almost 20 years. It is very powerful, but there's some limitations. And this is what we want to do with the seminar, is just sort of point out how to use it effectively, open that door, be comfortable with it, and also to give you a chance to share, what we know with you guys. And if you have things that come up with it, give us a call. Give us a call, send us an email. That's a big part of this. So that's it from my side, and I'll be muted and just be addressing questions.
Excellent. Thanks, George. So anyone that hasn't done one of these webinars with us, on the little toolbar for GoToWebinar, there is a questions section there. So punch in your questions. George will try to tackle those during the meeting, or if we don't get to you during the meeting, we'll follow up afterwards. And as always, feel free to email us. All right, so here is our general outline. There's two major categories of nonlinear analysis that we want to address. There's geometric nonlinear and there's material nonlinear. So geometric nonlinear, also called large displacement. We're going to address a couple specific examples like contact and buckling. For material nonlinearity, we're going to be focusing on plasticity. That's really the most common application of nonlinear materials. Also available is hyperelastic materials. It could probably be a bit of its own seminar, so we'll give you a brief introduction and when you might have to use that, but we don't have any in-depth discussion of that today. And once we kind of explore these two main categories of nonlinear analysis, we're going to move on and work through a bunch of different examples that will combine one, the other, both, incorporate some nonlinear effects into our standard linear analysis and vibration analysis. And then at the end we've got some gap element examples, compression only and tension only, great ways to model contact or tension only elements like cables, straps, chains. Here's our outline. When we sent out the announcement for this, this paper was just kind of a rough outline. You'll see today that it's a bit more complete. We have more examples and more information. So along with our webinar recording, this will be available online for you. Okay, before we get into nonlinear analysis, we need to do a quick recap of linear analysis. And the best way that I like to describe this is when we develop our stiffness of our structure. It's like a snapshot in time. And for linear analysis, you only get one snapshot right at the beginning. As you increase the load, as you apply more force, it's just this linear ramp and nothing changes. So you apply 10 pounds, 100 pounds, 1,000 pounds, you're going to get this linear stress-strain relationship, regardless of how much load you apply. That's where things kind of break down. That's not always going to be the most useful or accurate solution for us. What if we're getting plasticity? Well, we're going to have to incorporate material nonlinearity. The other thing that's important to note about linear is our stress is simply our force over our area. Our initial structure, our initial load path, that's what we get. So as things deform and change and the load path changes, we're going to want to update. And that's where the geometric nonlinear comes in. So this is a little bit of background. This is a good thing to keep in mind when you're running linear analysis and you see things that might be a red flag. I also wanted to mention this because before you ever do any sort of nonlinear analysis with your model, you should always run it linear first. Start simple, add these complexities to your model one step at a time. If you try and tackle a massive model with bolt preload and plasticity and buckling all at once, something's going to crash. And rather than hunting through all of these different wonderfully complex things you've added to figure out which one was the problem. If you add them incrementally, it's a lot easier to find the red flag there. All right, so this is my starting little example here, geometric nonlinear. Now, what I have in this example is a little plate. Imagine a ruler. It's an inch wide, about 10 inches long, 16-inch thick, and I've put a pressure load of 10 psi across this. Now, in the upper image, you can see the standard linear results as this thing deflects. In the image below, you see a nonlinear analysis where we've turned on large displacement. Now, it's very important to focus on the boundary conditions for this. I've got the edges, the far edges on the left and right pinned. So it's like they're on a hinge, but that hinge is connected to a perfectly rigid wall. So as we push down on this plate with a pressure load, it's effectively developing a hoop stress, and it stiffens the plate. So one side you see, oh wow, maybe this is what I've been needing all along to drastically improve my results. But on the other side, you have to consider, do you have a perfectly rigid connection? So we want to open up this door that nonlinear analysis can really affect your results and maybe provide you something more accurate. But on the other hand, you really have to think about your structure. You have to really criticize your constraints and think about what's really going on here. Quick little test that I did. Linear analysis gives me a deflection of 2.2, maximum stress of 190 KSI. When I switch over to large displacement, I'm only getting a deflection of 0.1 and a maximum stress of 24 KSI. So a huge jump. But as I investigated a bit more, I changed things around. When I switched over to a simply supported beam, the differences between linear and non-linear results were really pretty minimal. So we're not going to run through this example, but I'll have it included in our download package, and I recommend this as a great place to start. A real simple model, different boundary conditions, linear, nonlinear, and throughout all of this, this is just geometric nonlinear. We're not focusing on plasticity yet. Here's another example of some of the investigations I like to do for my models when things get tricky. I put a free body diagram right in the middle of this thing. So it's like we're taking a slice and looking at the forces transmitted from one half of the structure to the other. And you can see that in the linear analysis on the left, we've got a very large bending. It's pretty much pure bending. In the nonlinear analysis on the right, we're actually, pretty small bending moment, less than 5% of what we saw before, and we see a huge axial force. So like I said, it's almost like we're pressurizing this thing. It's curved. We're developing a hoop stress in this thing. Throughout this paper, you'll see a lot of quotes from the basic nonlinear user's guide. So up top, geometric nonlinear effects are prominent in two different aspects. Geometric stiffening due to initial displacements and stresses. That's what we see here. And follow forces due to change in loads as function of displacements. So we're going to investigate both of these different aspects of geometric nonlinear. I want to let that kind of settle in a little bit. We're going to come back and do another geometric nonlinear, but before we get into actually doing the modeling and doing the analysis setup, I want to do something a bit simpler. And this is actually going to use the linear solver, Solver 101, and we're going to incorporate contact. And we've included this, even though it's the linear solver, we've included this in our nonlinear seminar because when we're using contact, it's actually an iterative process to figure out which element faces are carrying compressive load, which element faces might separate, carry no load, and as it iterates through, it determines the load path, and really by definition, that's a nonlinear approach. What we don't have geometric nonlinear. We can't get anything to buckle or get any stress stiffening. We can't get any plasticity. But the upside is this is incredibly easy to set up. It's really nice. So I've got this pin clevis example. I've already meshed the model, applied boundary conditions, and you guys should be familiar with that. But I just want to walk through setting up the actual contact the connections at this pin-clevis interaction. A little bit of background here. Linear contact for Solution 101. We highly recommend checking out Chapter 19 of the User's Guide. It gives a lot of great background about how this works. We've got a whole webinar dedicated just to contact, and that'll help illustrate some of the pitfalls of setting up your connection regions and some general guidelines here. But these three images you see on the right, that's the general walkthrough of what we're going to be doing to set up our connections. So I'm going to open up this model. What we're going to include in our download package for all of these is a start and a finish model, just like we do with our training. So you can open up the start model, walk through these steps, and if you have run into any problems, there'll be a finish model with all the results there. So like I said, I've got boundary conditions, I've got mesh, I've got everything I need. I just need to get some interaction between the pin and the clevis. I should also mention that we see symmetry constraints here. So I've sliced this pin and clevis down the middle here and applied symmetry constraints. It's going to be easiest to get to the surfaces coming in contact if we can hide certain portions of the model. So I've already made some groups of the pin and the clevis. So I'm going to open up connections here. The first thing you do with connections is create a connection property, and this defines how the contact or how the glued contact will behave. So first thing I do, I hit defaults. Let's give it a title. And we're not really going to mess around with too much. Usually something I'll take a look at is our search distance. These parts are perfectly adjacent, so I could use a very small search distance if I wanted to. But in this case, the defaults are going to carry us through just fine. All right, so you see in the tree our first connection region, or sorry, connection property. Next, we'll create our regions. So this is going to be the two different sides of the contact. So new connection region, let's call this clevis. I'm going to pick by surfaces. And if you're working with solid elements and they're associated with geometry, you can pick by surfaces like this, and it's quite straightforward. If you're working with plate elements, or if you don't have geometry associativity, things get a bit more complicated. And usually it's within selecting your connection regions that troubles come up with contact. So if that's the case, again, check out our webinar on contact. So those surfaces make up the connection region for the clevis. I'm going to switch groups and do another connection region for the pin. Now, something that I asked myself when I was putting this together is, how would the results be affected? Do I need to select all of the outer surfaces of this pin, or just those that are initially in contact with the clevis? Now, for this example, I'll select all of these outer surfaces you see here. But again, you guys are going to have these models. I suggest coming back in, playing around with the connection regions and sort of seeing for yourself how this may affect your results. All right, I have a property, I have two regions. The last thing I need is a connector, and this will tie my property and my two regions together. We'll set up a linear analysis, and we'll let this run. Now, all of the models here I've tried to keep rather small. They should run quickly. In some of the cases where I have larger models, I've included those in the package as well, so you have the ability to explore. All right, something that you'll see if you've included contact in your model in the analysis monitor is the contact convergence. So the plot that you see here where our number of contact changes is dropping away rapidly with each iteration, that's what you want to see. If you can see this thing rising and falling, it means that it's having trouble determining exactly which element faces are coming in contact and gives you an idea that something might be wrong. All right, so we have our output set. We can deform and contour. And then we have our stresses. So you can see even with exaggerated deformation, the pin carries along here, transfers load. You can blank properties to take a look at the stresses inside your opening of the clevis. And you're also going to have some other output vectors that are available, like contact pressure and contact traction if you're using friction. All right, so this is our very introduction to any sort of iterative analysis. We'll come back to this example later. We're going to model this with gaps, which use the nonlinear solver, and we're also going to use contact in a few other scenarios where we can pre-stiffen our structure. All right, next geometric nonlinear example is buckling. Again, we have a whole seminar dedicated to buckling, but I just kind of want to narrow in here on the geometric nonlinear side. What's happening is this is going to be a large displacement analysis, and we're going to apply the load incrementally. And as we apply this load, the structure is going to deform. We're going to recalculate the stiffness of the structure and apply a bit more load. So it's going to be a step-by-step process. What happens is under compression, certain structures might actually lose stiffness. You apply a bit more incremental load, and you see a rather large jump in deflections or stresses. You do this again, an even larger jump in stresses and deflections, and that instability point, that's really what defines the buckling load of the structure. So we're going to model this simple Euler column here, and it introduces some interesting behavior because since we're doing since we're doing a numerical model of this, it's perfectly straight. And even in nonlinear analysis, we're going to have to take a few tricks with our boundary conditions to help encourage the buckling to happen. Quick screenshots of the nonlinear control, our analysis monitor, and some charted results. So the key here in the nonlinear options is requesting all intermediate output. That way we can plot the deflections and the stresses as the load is applied incrementally. The analysis monitor provides some nice information because you can actually watch incremental loads being applied as a function of the iterations. So this plot here shows getting up to 90% of the load, seeing some instability, and you can actually watch the solver struggle through trying to reach the full load. And then the last is the charting option here. So again, referencing back to the user's guide, it's recommended to check all possible buckling modes with the linear buckling solution first. You may have to introduce some initial imperfections from loads or displacements to keep the structure in the intended buckling mode. So that's what I'm saying. We've got a numerical model. This beam is absolutely perfectly straight, zero imperfections. It doesn't matter how much we press on this thing, even in a nonlinear analysis. It's not going to buckle to the side. So I'm actually going to instigate the buckling with a little bit of bending moment here. We can play with the bending moment to see exactly how much it takes. All right, this is Euler buckling start. Here it is. So the first thing I want to run is a linear buckling analysis to give me an idea of what might happen and what sort of loads might cause this structure to buckle. So this is analysis type 7. We're just going to use loads and constraints like we would for a linear static analysis. It's going to provide us with two result sets, the first being a linear static analysis, and the second giving us a buckling factor. So I'm applying 10,000 pounds on this thing. The bottom of this is constrained in the X, Y, and Z, and then also rotations about Y. We don't want our column to spin about its axis. And then up top here, we've got this constrained, there we go, we've got it constrained just in X and Z. We don't want this thing to tip over. So I've tried to mimic the constraints that we see in this image here. All right, let's look at our results. So it's telling us that we have a buckling factor of 5.75. So multiply that by our applied load, we would have a buckling load of 57,500 pounds. Now if I'm going to do a nonlinear analysis, which is option number 10, nonlinear static, as I mentioned, I want to come to first bulk data entries, large displacement. By default, that's going to be turned on, and that's what we need to capture these nonlinear geometric effects. The next thing I need to do is come to the nonlinear control options page. Now, even if you're not going to modify anything on this page, you actually have to click through until you reach this page, and I think it effectively sets the defaults. If you create a new nonlinear analysis, click OK and run, it'll tell you that you haven't set your nonlinear options. So you always have to come visit this page just to set the defaults. But in this case, we actually are going to modify. We're going to request all intermediate output, and we could set the number of steps. By default, it will be 10. If we want more resolution, we can request more steps or more increments. So the next thing we need to do is we actually have to increase our load, because since this structure is going to buckle at 57,000 pounds, our linear or our nonlinear analysis is only seeing 10,000 pounds. Nothing's going to happen. So I'm going to come in here, modify my load, and I'm just going to bump it up by a factor of 10. The other thing I need to do here is to instigate the buckling. And in our buckling white paper, we discuss a variety of different methods, whether you add some imperfections to the model or apply some loads to help this happen. I'm going to use a little bit of bending moment right here, and I want to put a moment about the x direction, and I'm going to start with 100 inch-pounds. So now let's run the nonlinear analysis. We get a fatal error, which in this case, not such a bad thing. We've reached this instability where the solver has crashed, and that's letting us know that it has buckled. We could take a look at our nonlinear history, see our load incrementing up, hitting that portion, and never really being able to converge. And then in the output set titles, we can actually see our load value. So we increment up 10, 20, 30%. We get to about 0.57 of our total load. The analysis has crashed. That's our buckling. Now, something that I want to talk about, it'll be a bit of a self-study, is exactly how much instability do we instigate in the model. You know, what if my bending moment was 10 pounds, or what if it was 1,000 pounds? And what I've found in this model is if you start low and work your way up, you can actually converge on a value that will mimic your hand calcs or your linear buckling analysis. You get to a certain point, it doesn't have a huge effect on the results even if you increase this moment load. But you want to be aware, or you want to check your reaction forces and keep an eye on your buckling load, because, you know, if I apply 10,000 inch-pounds of moment here, I might actually be a bit overly conservative because I'm putting more bending in this beam than I really need just to instigate the buckling. All right, moving on. Like I said, we're going to have a quick pace through this this workshop. So if you got any questions, feel free to chime in. Okay, let's move on to material nonlinearity. Now, the first thing that I want to talk about is kind of how we tie from geometric nonlinearity to material nonlinearity. Again, from the user's guide, stresses and strains of small strain elements, and small strain elements is basically everything you're going to see in this webinar, unless you're using hyperelastic materials or working with small strain elements. So the stresses and strain of small strain elements refer to the undeformed area and length respectively. So what this image shows is how, with large displacement, we're tracking the translation and rotation of elements through space with a large deflection analysis, but we're not updating the element area in terms of stress calculations. So this ties into material nonlinearity, because since we aren't updating our element areas, that means that we have to use engineering stress-strain curves when working with these elements. So again, large deflection captures the translation and rotation, but it doesn't capture the change in area. Before we get into our first nonlinear material example, let me just bring up a quick example model. And if I go to material, nonlinear, I did a quick little pull test here to kind of test this theory of small strain, large strain. So the first thing that I have is a static analysis. And if I use entity info in my selector, I can take a look at the stress in my elements. So with a linear analysis, I'm getting a nominal stress value of 45 KSI. Now if I switch over to a nonlinear analysis, I've got plasticity. You can see this thing narrowing out here between the linear and the nonlinear. In the nonlinear, we're getting more elongation, and our cross-sectional area is reducing even more. But if you look down here in the entity info, our nominal stress value is still sitting at 45 KSI. So that's kind of how this small strain works, is even though we're reducing our cross-sectional area of this bar, the stresses are still calculated based on that initial area. I've got some more notes in the back of this paper that kind of discuss this small strain, large strain a bit more. But let's move on to our material nonlinear. All right, so we have a 4-point bending test. As you can see here, I've chopped it down to quarter symmetry, and we're not really going to be modeling contact between the fixtures and our little plate here. We're just going to be applying symmetry constraints, a simple support, and then applying our load, like you can see here at this fixture. But what we really want to focus in on is how we're going to model our nonlinear material. So for this example, I'm assuming A36 yield stress, 36 KSI, ultimate tensile at 60 KSI, and a 20% strain at failure. So to keep it simple, those are really the only pieces of information I need in addition to my elastic modulus to get a nonlinear material model. So as I mentioned before, we're going to start with a linear analysis just to make sure that our model's set up correctly. We've got boundary conditions, we've got loads, so let's run that. And we want to make sure that the stresses in the linear analysis actually exceed yield stress, otherwise I wouldn't have any material nonlinearity. So here's the results. Let's deform and contour, and I can get rid of my geometry and boundary conditions. There we go. So we're getting close to 60 KSI. We're definitely exceeding the yield stress. So we want to incorporate material nonlinearity. First, I'll set up a nonlinear analysis. And everything is going to be fine with the defaults here. You can do a little investigation to see if large displacement is going to have a significant effect on this analysis or not. Run it with, run it without. The advantage of having a small, quick-running model. And like I mentioned before, visit the nonlinear control options page to make sure that you set the defaults. All right, now for our material. There's two different ways that we can model plasticity. And the first way that I'm going to show you is to set up a stress-strain curve. Now, it's not my preferred method, but I think the bit more intuitive, and it kind of provides some information about how we would set it up the other way, the bilinear way. So we're going to say a new stress strain function here, and we can call this engineering stress strain, and we're just going to punch in our values. So 0 strain, 0 stress. At our yield stress, 36 KSI, we can use Hooke's law to calculate our strain. So if stress is equal to modulus times strain, that means that strain would be equal to stress divided by modulus. For steel, 29 million. We can add that point there. And then our last point here is going to be at failure. So we're going to say 60 KSI, and strain at failure, as mentioned, is going to be 20%. There you go. So I'm using this to kind of illustrate because we're going to need these data points for our next material model. We come into our material, come to nonlinear. We're going to choose plastic. We're going to pick our function, and we're going to enter our yield stress. That's all we need. So now let's run our nonlinear analysis. This one's going to take a little bit longer than the linear analysis. So while that's running, I'm going to set up my alternative nonlinear material technique. And that alternative technique is elastoplastic. And when we turn this option on, you can see that our function disappears here. All we need for this is our initial yield stress and our plasticity modulus. So it's called bilinear because you're really just breaking the material behavior into two regions, the elastic region and the plastic region. And if you were to look at our curve, we just have two straight curves, two linear curves. So this first curve, that's just our elastic modulus. We know the slope of that. So what we want is the slope of this curve here. And our strain at yield is very small. I'd say it's negligible. So all I need is the rise, which is the difference between yield and ultimate, over the run, which is the difference in strain. And that'll give me the slope of that curve. So let's come in, edit. We're switching here. So again, rise over run. Rise would be 60 KSI minus 36 KSI over the run, which is 20% strain. And I'm just going to go back in here and double check to make sure that Femap has done my math for me. No, I did my own math wrong here. Let's try that again. 60 minus 36 divided by 0.2. One too many, thank you. There we go, positive number, that is a good thing. So as you can see, the slope of our plastic region is less than the slope of our elastic region. All right, so this is chewing away here. You can see as the load increments, we get up to about 80%. We're starting to see some plasticity, and the nonlinear solver is working its way up, trying to find convergence on a final load here. So since this is choking along and we're on some time constraints, I'm going to do what I call the cooking show method, where we put something in the oven and then automatically pull out something that's done. And we'll take a look at the results here. All right, so what I've saved is a variety of result sets here. Like I said, it's good to investigate. Does large displacement have a significant effect on these results? So first, our linear results, stresses at about 58 KSI. We bring in the plastic, this is with our stress strain curve. We could deform this, and we see stresses at about 39 KSI. So we're exceeding yield in this region. You can see a larger portion of the bar is getting engaged. The stresses are flowing a bit more. And then we could switch over to our elastoplastic, which is the one that I just set up. And you can see that results are effectively the same. Come in and check the large displacement, and our overall stress values are actually slightly reduced. So you'll have to think about the effect of follower forces here. Being simply supported, we're not really getting any sort of stress stiffening. You just want to be aware that as this thing sees larger and larger deformation through plastic, the stiffness of the structure is going to change a bit more. So this is complete with both large and small displacement and both nonlinear material options. All right, hyperelasticity. So this is really the element type and material type that captures the true nonlinear behavior. Not only are we getting elements translating and rotating through space, we're also getting a true update of material or of element area and length. Some guidelines here, again from the Nastran documentation. If stretch exceeds more than 20%, it is recommended to use hyperelastic elements if applicable. Some other things that are nice here. In areas of the structure where large deformations are expected, the mesh must be fine enough to keep element net deformation small. So you might have to refine your mesh to make sure that you're not getting extremely distorted elements. And then, again, some guidelines about element strain and total deflection, where you might consider this being used. Now, if this is something that you think is going to be applicable to your problems, feel free to contact us. We can help you out. We just don't have time this hour to dive into these. They're a bit more complicated than our plastic model. All right, moving on. I want to come back to our linear solver here. We've already worked with contact, but I want to introduce the idea of multi-step analysis, where we actually stiffen the structure before we apply our operating loads. And the way this ties into linear analysis is contact with bolt preload. I've got this shaft. On either end, it's supported by a little bearing and a pillow block, and that's mounted to this pedestal here. So first we're going to run it, no contact. Then we're going to sort out our bolt preload. And then finally we're going to tie it all together, stiffen it with bolt preload, and then run the static analysis of the stiffened structure. This same approach can be applied to a vibration problem, and we'll be running the vibration on this same structure here. Now, unlike the static linear solution, normal modes analysis can't incorporate contact. And this is a bit confusing because we're getting this stiffened structure. Obviously, it's incorporating contact somehow. And I just want to clarify that we're using the updated stiffness, the differential stiffness of this bolted clamp structure for vibration analysis. We're not really getting contact during the vibration event, and the way I describe this is you can't simulate a clapping event where a metal bar would be vibrating and slapping into a neighboring component. That sort of contact isn't going to work here, but we can get this subcase where we stiffen the structure ahead of time. So let's open up this model and work through it. I'm going to close some of these others. Here we are. Since this is sort of a complex assembly, I've gone in and I've already set up the connection regions. So if you were to turn off the elements, you could see the connection regions here. And the first thing I want to do like I said, we're going to analyze it with no contact. And I don't have to delete out these connection regions. I can simply deactivate them. So I'm going to select, I can even highlight, I'm going to select everything here but the bushings and say disable. Now I'm leaving the bushings in because they're a glued connection. There's no bolts, fasteners, or any of that. I need that glued connection to keep the bushings in the pillow block. Otherwise they would just fly away. All right, so I've disabled my contact. I'm going to run a static analysis. And this will sort of be our baseline. The next thing I'll do is I'll enable the rest of this contact, and we will take a look at a linear analysis with contact. All right, so that's complete. I'm going to enable all the connectors, and I'll let that run. So while this is running, let's go ahead and set up our bolt preload. I always like to use bolt preload as its own load set, so I can sort of differentiate it or use it across multiple load sets. So we're going to create a new load set here. Call this bolt preload. The other thing that this allows me to do is test out my bolt preload before combining it with other loads. I'm going to want to just show my beam elements. Actually, we'll just show our bolt property. There we go. And my load type is going to be bolt preload. Now I've calculated out for this size of bolt we want 30,000 pounds of bolt preload. We'll give this a title. And we will select the elements we want this to work with. Go. All right, so my next analysis is done. So let's fire up this next one here. Now what I want to do with this one, like I said, you can see we've got our constraints, our loads. I'm going to switch my loads, just looking at bolt preload. And while that's running, we'll do a little bit of model organization. So first output set, operational load, no contact. This is operational load with contact. So let's look at those. And I believe that the differences in these should be quite apparent. We can see the elements passing through each other, lots of bending in the fasteners there. When we switch over and enforce contact, the stress profile and the deflections change quite significantly. So what we want to see is when we incorporate bolt preload, we still have contact between parts. Nothing's flying off into space. Stresses aren't exploding. So I believe this is working correctly. Let's call this bolt preload with contact, which is a bit redundant. You cannot run a bolt preload analysis without contact. The bolts would cinch up, the parts would pass through each other, so be aware you always need contact to use bolt preload. So now we want to tie everything together. Coming back to my boundary conditions, I'm going to use my operational loads here, and this is how I'm going to incorporate bolt preloads. Is down here I can select my bolt preload load set. We'll analyze. So this is really going to run through two complete analyses. First, it's just going to look at the bolt preload, find contact faces, cinch everything down, and update our stiffness. Then it's going to apply our operational loads to this new stiffened structure, and it's going to give us something that should be different from both our previous output sets. All right. I mentioned that we can incorporate this same sort of effect with the vibration analysis. So in this model, I've set up a normal modes analysis. We're going to want to run this with and without the bolt preload to get an idea of what sort of stiffness we're going to get from incorporating this into the model. Let's take a look at our final results. Okay. Oh, and our original one's done. So this is uploads plus bolt preload with contact. There you go. So no contact, with contact, and with contact and bolt preload. So it's less significant jump, but we're still dropping stresses from 43 KSI down to 37 KSI. And we're reducing the overall deflection by 0.04 inches. Depending on your application, that could be pretty significant. So this is another example of slowly building up the complexity of your model in increments. All right, let's move on to the normal modes analysis. Now I'm going to analyze this one. It's going to ignore the contacts. It's just a standard normal modes analysis. And for this one I've gone in, I've just requested the first 5 natural frequencies. And things get a little wild in these higher frequencies, but we need this as our baseline. So to incorporate bolt preload into this, it's actually really simple. You want to expand the analysis for your normal modes. Come down to the bottom here and we're going to add an additional case. So we simply add in bolt preload. It'll use the constraints from the master requests and conditions. And we hit analyze. Now this is something that in some models I've seen a real significant jump. In other models, not so much. With this one here, I think we saw a pretty significant jump, especially in the first few normal modes, because we just have 2 bolts in line with each other. So as this shaft moves up and down without any sort of contact or bolt preload, the stiffness in that direction is really highly dependent on the bending stiffness of those 2 bolts. Once we incorporate contact and bolt preload, we're actually getting the interaction between the pillow block and the pedestal and transferring, the load a bit further out from that center line of that bolt. All right, how are we doing on questions, George? Everything going well there?
Hi, Adrian. Just a few questions, and more like, are you using the iterative solver when you're using the contact sequence?
Oh, yeah.
I think you are.
Probably the way this one's running, I probably did not turn that on. It would probably be significantly quicker if I did.
Well, it might not. It's a mixed bag of contacts.
It's always tough to tell, especially with rigid links and beams.
Yeah, I don't know. That's why I build small models and try to debug all the mechanisms you can quickly before doing something really big.
Okay.
And then, are you using on your connection properties? You're only using one connection property, aren't you?
For this one here, I've actually set up 2 connection properties. Glued was
glued. Yeah, that's what.
Glued was
so
just
there's a little note that you can set up different contact connection properties, but NX Nastran only grabs a subset of options within it. For example, open up your contact with friction. Mm-hmm. So the solution parameters, for example, max force iterations, max status iterations, that's for the whole analysis. So even if you have another connection property card, it can't change that because that's for the whole solution. But what it can do is it can use different friction values. Mm-hmm. So if you want to vary friction,
it's just this
different components.
This upper box and this lower box that changes with each property.
Yeah, but it'll give you a little warning message. And if you want to know more, again, NX User Guide, Chapter 19.
Mm-hmm. All right, let's plow ahead here. So, all right, first mode, we're jumping from 38 hertz up to 44 hertz. Second mode is really, it's not, I would say it's almost orthogonal. We have a little bit of different stiffness because of the way the pillow blocks are set up. A huge jump here in the third mode there, and you can see that's really dependent on the bending stiffness of those bolts. Once we've incorporated bolt preload and contact, we jump from 60 hertz to 115. So massive increase in stiffness there. You know, this is huge. I would say this is uncommonly large to get this sort of jump, but you know, it seems like a real-world problem. These components exist. This is a typical setup, so depending on your application, you might see something this dramatic. All right, what do we got next? Residual stress. So this kind of takes this multi-step analysis method and incorporates it into the nonlinear solver. Earlier we pushed on our beam here, our 4-point bending. We got it to plastically yield. But what would happen once you removed the load? You know, how much residual deformation and stress would it have once you pulled this thing out of the test fixture? To do this, we can pick up where we left off, and we can really just add a subcase like we did with this natural frequency analysis. So I'm going to say 4-point bending test. Let's take a look at what we've got here. We've got loads, constraints. What I need to do is I need to have a load set for my unloaded state. And Femap will actually bark at you if you apply a 0 load. So I'm just going to apply a very, very small load. I'm just going to apply the same nodes. Actually, I think we need, there we go. Come on now. We could always, rather than fumbling through this, I'll just copy this one over and modify it. So let's update the title. Let us know that this is unloaded. Force on curve. Like I said, I'm going to just do something very small. 1 e to the negative 6. We come into our nonlinear analysis, and we can add additional cases here. So the first case is going to use our full load set 1. Our second case is going to use our unloaded load set. And you can see I'm leaving the constraints blank here because we can use the master requests and conditions. So I'll come in here, constraints, I'll use the same constraint set throughout, and I'll just blank out the loads here. All right, let's analyze. Now, this is just one example of this multi-step analysis, but really the same technique of using multiple steps can be applied to a variety of different conditions, whether you have some sort of pre-tension, press fit, shrink fit, some sort of thermal load that might stiffen the structure. All of these can be applied in subcases. Each subcase can have its own set of boundary conditions. So you can really, you're just taking more snapshots in time, and it's giving you the opportunity to affect your boundary condition in each one of these snapshots. All right, let's take a look here. We've got this guy loaded up to max. It'll converge on that one, and then we'll see our next unloaded state. All right, so we've got we've got about 5 minutes left. I've got 2 examples. I think we might have to save. What do you think, George? We've got gap contact and we've got tension-only cables here. Both of them use gap elements, and it's all about setting a different compressive or tensile stiffness for our little gaps.
I want to vote for the gaps because it's really useful. They're a great little element to employ. And I want to also mention one thing too, and all this nonlinear in solution 106 is that we're using small. The trick on Nastran is that they're small strain element formulation, meaning that it's a simplified formulation, and it doesn't handle large strains very well. Large strains really greater than 10%. It's problem dependent. It's just one of those things on that side, on the solution 106, and it is why NX Nastran has an advanced nonlinear solution 601. So what we want to cover on this is really what you can do with the 106. Mm-hmm. And if it doesn't seem to quite work for you, give us a call and we can talk about the solution 601.
Yeah. And I think this gap problem here is kind of a good introduction to that as well, because, all right, originally we had modeled this in the linear solver, real easy setup, surface-to-surface contact, click go, it's pretty straightforward, but we're not able to incorporate plasticity. If you want to incorporate plasticity, you're going to have to use either the static nonlinear solver 106 that we've been using today, or like George mentioned, the advanced nonlinear. Now, the tough part about using 106 is it does not support that surface-to-surface contact, that easy contact setup. So if you need to include both contact and plasticity, you're going to have to spend some more time up front modeling. And what you'll see in this part here is the mesh on both the clevis and the pin are perfectly matched. There's a node-to-node alignment there. For every node on the interior face of the clevis, I've got a node on the pin. And that allows me to snap gap elements between the two.
Right. And I want to mention that this is an extremely powerful technique. It runs super fast, and it's what we use for Boeing's landing gear set on the 787, the Dreamliner. And it just smoking fast. It's really the fastest sort of contact setup you can ever get using that sort of alignment. And Femap really facilitates this. It's really preferred, and it gives you great results. It just takes a little bit more upfront time modeling.
Yeah. So the technique I used, well, let's wrap up on this one. You'll see we have
and then jump on the cable so we can close out some more.
So here's
mute.
Case 1 and case 2. So we have our fully loaded and our unloaded states here. So zero load, you can see the residual stresses, residual deformation. But the tool that really makes things easier with the gap elements, I think, let's go ahead and open this up. First of all, I like to work with groups. And in this one here, I have created a group of nodes on the clevis. So let's take a look at that, turn on. And you can see those are just the nodes on the interior face. Not sure if you can see those. Those are the nodes on the interior face of the clevis. And another group of the nodes on the pin. So I can use mesh, connect, closest link, and I'll take advantage of these groups going from the clevis to the pin, and then I can pick gap elements. This also works well for rigid elements, beam elements, whatever you need to snap in there. We'll snap these in. We'll choose an orientation vector, which has to be orthogonal. So these are all running radially, so I would want the global Y direction, I believe. There we go. If we really zoom in here, you can see how it's snapped in node-to-node connections for all of us. So let's quickly talk about our gap element property, because this is what differentiates my contact from my cable. So here we've got our gap element. A very high compression stiffness, and there's guidelines on what sort of compression stiffness you should use in the Nastran documentation, and a very low tension stiffness. A little bit of tension stiffness helps stabilize the model, but you don't want it to carry much tensile load, so that's a small value. So what we've got here is these springs, but they have different stiffness whether they're in tension or compression. You need to make sure that your nonlinear analysis has large displacement turned on. This is a geometric nonlinear effect. It's not going to know if these are in tension or compression until we apply incremental load and update the stiffness matrix. However, these are not large displacement elements. That means if your two contact surfaces see large rotations or displacements with respect to each other, the orientation of these gap elements is not updated. So I think there might be, a more eloquent description of that in the help guide, but be aware that when you're using this contact, you want these two faces to kind of translate or rotate together. It's not like a spinning, sliding friction contact. You want it to be rather static. Just because if these elements really start to rotate a lot, they're not going to update the stiffness based on their new orientations, and you're going to get some odd results there. So you need large displacement turned on, but at the same time, you don't want to experience large displacements between your contacting bodies. I think that makes sense. I hope that makes sense. Okay, so just like this, this model here, using high compression, low tension, I've done the same with our last example model of the day, and that is our radio tower. So here, I've stiffened this little spindly radio tower with guy wires. So let's take a look at these gap element properties. I've created a different property for each length. The longer cables are going to have a bit more compliance. Given a very low compression stiffness and a tension stiffness based on the length and diameter of my cable. So you can see each of these has a different tension stiffness. And I compared linear and nonlinear runs. The linear run here this was before I had incorporated the guy wires. You can see massive bending moment at the base, just effectively a cantilever beam there. Once I incorporate the guy wires, my bending moment drops like crazy. I get big tensile reactive forces at these two. You can see the direction of the load. And I get nothing at this one. They're going into compression. They're effectively going slack and not carrying any load. So again, the usefulness of free body diagrams comes through to help you debug the model. All right, wrapping up on our whirlwind. In the paper here, I've put in an appendix of do's and don'ts. Number one is rigid elements. Be very weary of using RBEs with any sort of large deformation. The degrees of freedom of a rigid element, they're not updated as it rotates and translates through space. So avoid your rigid elements for large deflections. It can give you ridiculous results. We actually had a model we were looking at earlier this week. Beautiful, simple model, and we're sitting there looking at it. What's going on? These results aren't quite right, and the RBE2 was our smoking gun. That kind of expands to offsets. If you're using offsets with your beam elements, those aren't going to get updated as things rotate. So you're going to want to.
I want to jump in because offsets use RBEs to enable the offset. Mm-hmm. And all this is covered. We have another technical seminar on connections and RBEs, or multi-point constraints. And they're set up creating constraint equations within the matrix. And so being linear, they're created at the start of the analysis. And so when you do anything that's geometrically nonlinear, you're screwed. I mean, it'll work sometimes, just enough you think it might work. and they'll nail you.
It'll behave just well enough to earn your trust.
Then just like boom. And it's not any big deal. The workaround is you just use beam elements.
Yeah.
And there's a nice little API that will swap out your RBE with beam elements. So.
Okay.
Moving on.
The Femap, or sorry, the Nastran documentation here that I referenced a lot for this paper was the Basic Nonlinear Analysis User's Guide and this handbook. And so what I did is in this directory here that I'll be uploading for you, I just downloaded these because if you get to this through the Femap help, it opens in a browser and you'll have to switch browsers. And anyways, it's easiest just to download the PDFs. But I've gone through here, and sections that I thought were particularly important to note, I have highlighted. You'll see probably a lot of this quoted in the paper itself, but I couldn't copy and paste this whole thing in here. So sections are highlighted. Things that I think are important to note when you're working with nonlinear analysis have been pointed out here in this document. And it's 140 pages, but a lot of it are example models. A lot of it's bulk data entry, so it's not that bad. It's a manageable size, and it's worth skimming through if this is going to be a tool that you're using.
Okay, 3 minutes.
All right. Yeah, thank you everyone for hanging around for this extra time. Again, this will be online. You can slow it down. You can ask me questions, email, and have fun with these models. So, excellent. I think that's everything.
That's it. All right. Have a good morning, everyone.
All right.
Take care.
Thank you all.